the first thing I need to do is work out the distance travelled by ship A and the distance travelled by ship B after 30 minutes. The distance, you should remember the formula for distance is speed multiplied by time. So if I want to get the distance that ship A has travelled, its speed is 15 kilometers per hour, and after 30 minutes, remember the speed is in hours, so we convert the 30 minutes to hours, so the time is a half. 30 minutes is half of an hour. So after 30 minutes, 15 by a half gives me 7.5. Ship A has travelled 7.5 kilometers. To work out the distance that ship B has travelled, it's the same thing. It's the speed, which is 30, multiplied by the time, which is a half. 30 by a half tells me that ship B has travelled 15 kilometers. Now that I know how far ship A has travelled and how far ship B has travelled, I can come up with a triangle and work out the distance from A to B. So let's just draw ourselves a triangle here. So I'm going to draw this line to represent the path of A, this line to represent the path of B, and this line represents the distance between the two. So this is where A was. The ship A started here, but it is now here. Ship B, it started here, but it has travelled, and ship B is now here. So the hypotenuse of this right angle triangle represents the distance from A to B. I know the distance that ship B has travelled after half an hour is 15 kilometers. So that distance is 15. And I know that the distance from A's original position to B's original position was 90 kilometers. But if ship B has travelled 7.5 kilometers, it's no longer 90 kilometers from that place. It's now 90 minus 7.5. So this distance is now 82.5 kilometers. So it started off 90 kilometers away from here, but it's now only 82.5 kilometers away. And from here you should recognize I can simply use Pythagoras Theorem. If you know two sides in a right angle triangle, to get the third side you just use Pythagoras. I can say that AB squared must be equal to 82.5 to be squared plus 15 to be squared. And I'm just going to plug this into my calculator and I'm going to work out a value for the distance AB. So if you plug 82.5 squared plus 15 squared into your calculator, you get 7,031.25. You get the square root of both sides. The distance from A to B after half an hour is 83.85 kilometers. In part B, we're told that T represents the time in hours after the ship sets sail. And we're asked to prove that the distance between the two ships is, and then we're given what looks like a very intimidating, complicated expression. What you need to do is exactly the same as what you did in part A. It's just that instead of taking the time as a half of an hour, you take time as t. Other than that, the maths is literally identical. So I want you to just compare what we're about to do with what we did in part A. In order to work out where A is after t hours, we'll just do exactly what we did in part A. In part A, the first thing I said was, well, distance is speed multiplied by time. And I worked out how far A had travelled, because the key was the distance from A to B at the start of this scenario is 90 kilometers. And A is travelling at 15 kilometers per hour. So the distance it has travelled after t hours is its speed is 15 and the time is t. So the distance it has travelled is 15t. In part A, that figure was 7.5. And to work out the distance from A to the original point of B, in part A, I got 90 minus 7.5. This time, I'm going to get 90 minus 15t. The distance, so if this is the original scenario, after t hours, A is moving along that horizontal line. The entire thing is 90 kilometers, but the distance it has travelled after t hours is 15t. So to work out the distance from A to the new position of A to the original position of B, it's 90 minus 15t. That's the distance it has travelled after t hours. That's the distance it is from there after t hours. I calculated that in the exact same fashion as I calculated the 82.5 in part A. I also need to work out where is B, because B is now down here somewhere. It's travelling vertically downwards. So the distance, to work out distance, it's speed by time. D's distance, speed, is 30 kilometers an hour, and the time in this case is t. So the distance that B has traveled, distance for B, is 30t. B is no longer where it was, it's now down here somewhere. Let's say it's down here, and the distance it has traveled is 30t. So this is the right angle triangle. It's exactly the same as what we did in part A, it's just our distances are in terms of t. Last time I knew the distance B had traveled was 15, so I had a 15 here. This time the distance it has traveled is 30t. Now I'm no longer concerned with that, the original point of A. What I am concerned with now is the distance from A to B. And I'm simply going to use Pythagoras Theorem. And so I want you to notice we just do literally exactly the same as what we did in part A. Once we use Pythagoras Theorem here, we're going to get to our answer. I want to work out the distance from A to B. So I'm going to use Pythagoras. Obviously in this case the hypotenuse is the AB. I can say that AB squared is equal to 90 minus 15t to be squared plus 30t all to be squared. So this is just AB to be squared. Now, 90 minus 15t, you just multiply it by itself. If you multiply 90 minus 15t by 90 minus 15t, you're going to get 8,100 minus 2,700t plus 225t squared. 90 minus 15t, if you multiplied out your double brackets, you'd get these three figures. And then 30t multiplied by 30t, in that case it's going to work out as 900t squared. And at this stage you should notice that the answer we're trying to get to, some of the numbers are looking familiar. So this is 8,100 minus 2,700t, 225 plus 900 is 1,125t squared. But always write your answer in exactly the way that they asked you to display it. Obviously I don't want AB squared, I simply want the distance AB. So what I would usually say is get the square root of both sides. However, in this case, just purely because of the way it's written in the question, I'm going to write everything to the power of a half. The left hand side to the power of a half is just AB. The right hand side to the power of a half, I will literally just rewrite it exactly as it is, and then I'm going to put it all to the power of a half. And if you compare what we have here to what we were asked to prove, this is our final answer for part B. In the final part of this question, we're asked to work out the value of t for which there's the shortest distance between the ships, and then find the corresponding distance. We were told to use calculus here. In part B, we worked out that the distance between the ships in terms of t is this. Now, when you see the shortest, or the smallest, or the biggest, or the longest, or any extremes, we're talking about maximum and minimum points. We want to find the shortest distance, or the smallest possible value for this function. What that means, you should think of your differentiation, think of the tutorial we did on maximum and minimum points, and you should think about working out the minimum point. In order to work out a minimum point, you get your first derivative, which represents the slope, and you let the slope or the first derivative equal to 0 and you solve for t. So that's exactly what we're going to do here. If I know s of t is equal to this, the first thing that I want to do is get the derivative s dash of t. Now, in order to differentiate this, we're going to use our chain rule. So the first thing you should do is just view this as just one term to the power of a half. Like, imagine if I asked you to differentiate x to the power of a half. If I asked you to differentiate x to the power of a half, you first bring your half in front, you get a half times x, and you would decrease the power by 1. A half minus 1 gives me minus a half. So the derivative, that's the first thing we're going to do in our chain rule. If I'm just viewing it as this term to the power of a half, which is going to become a half times the entire bracket, and then I'm going to change my power by decreasing the power by 1. If it was to the power of a half, it's now to the power of minus a half. Now, once we've done that, we also have to multiply by the derivative of what's in the brackets. So we've dealt with the power, but now we need to deal with the derivative of what's in the brackets. The derivative of 8,100 is just 0 because there's no constant there. The derivative of minus 2,700t is minus 2,700. And to differentiate 1125 t squared, you bring the 2 in front. 2 multiplied by 1125 is going to give me plus 2250. And instead of t to the power 2 becomes t to the power 1. So that's you're just multiplying by the derivative of the algebra. To simplify this, we need to really think about our rules of powers. Here I have 1 over 2. So basically what I want to do now is I want to write all of this as a fraction. And there's going to be a 1 on the top and a 2 on the bottom. So the 1 over 2, that's where it comes from. On page 21 in the maths tables, it tells me that a to the power of minus p is the same as 1 over a to the power of p. So if I have something to a negative power, I can simply bring it underneath the fraction. I can bring it underneath and make it a denominator, and the power of it changes. Instead of to the power minus p, it becomes to the power plus p. So with that in mind, I'm going to take this entire bracket that's to a negative power, and I'm going to write it underneath. It's going to be 8,100 minus 2700t plus 1125t squared, and it's all of that to the power of plus a half. Instead of to the power minus a half, it's down to the power plus a half, just using that rule of powers. Now, I just am multiplying then by all of this over 1. You should just, this is just a number. You're just multiplying by minus 2,700 plus 2250t. So that's just going to be on the top. I don't have to do anything fancy with that. There's no powers there. So you just literally write it on the top. So this is just a lot tidier. The 1 over 2 is simply here. All of this that was to a negative power is on the bottom. And then this bracket, it goes on the top. That's the derivative. And in this case, I want you to think of it as the slope. I'm trying to find the shortest distance between the ships. And in the context of differentiation, that means you're trying to find the minimum value of this function. To find the minimum value, you let the slope equal to 0. So I'm simply going to let this equal to 0. Now, I can make my life really easy here, because what I'm going to do is I'm going to multiply both sides by the entirety of the bottom. If I multiply the left-hand side by the denominator, the top is simple. I just am left with minus 2,700 plus 2250t. If I multiply the right-hand side by the entire denominator, anything multiplied by 0 is simply 0. So that's handy. Basically, you can just completely eliminate the entire bottom of your fraction, and now we just have a really basic equation that we can find a value for t. You add 2,700 to both sides, and you divide both sides by 2,250. If you plug 2,700 divided by 2,250 into your calculator, time works out as 6 over 5. 6 over 5 is simply 1.2. So that means the time after 1.2 hours, the ships are as close as they will ever be to each other. Based on what's going on here, after 1.2 hours, the ships are as close as they could possibly be to each other. However, there's also another part. I've also been asked to work out the actual distance. So think of the tutorial we did on maximum minimum points. Usually you find your x value and then you sub back into the original function to find the corresponding y value. In this case, instead of x, I have t, which is time. And in this case, instead of y, I have s of t, which is the distance. So now I'm going to sub in t equals 1.5 into this function, and that's going to tell me the corresponding distance, how close the ships are after 1.2 hours. And that is the smallest value for the distance that I could possibly get in this function. So the final part then is quite straightforward. Instead of t, you sub in 1.2 in each case. When you plug it all into your calculator, to one decimal place, the closest between these ships will ever come is 80.5 kilometers. And that's your final answer for part C.